Hi everyone, welcome to the fourth video in our thermochemistry unit. This video is going to focus on how we actually calculate enthalpy, or delta H. So in the past video, we talked about two different methods. We talked about looking at delta H experimentally using calorimetry, and then we talked about calculating delta H using Hess's law, which is using known values of delta H from different reactions. So in this video, we're going to look at calorimetry as well as Hess's law and actually look at calculations. So the first method to find delta H, looking at calorimetry, this is at a constant pressure or constant volume. And when delta H equals Q, we can use Q like we did last year. Use Q equals MC delta T. When we have Q equals MC delta T, M is our mass, C is our specific heat, and delta T is our change in temperature. Q equals MC delta T is on your AP equation sheet, so you will have that. And another very important piece of information from this is that the heat lost, so negative Q lost, is equal to Q gained. Typically this is negative Q of reaction equals Q of solution, but it is important to remember that any heat that is lost is equal to the heat gained. And the specific heat of water and most aqueous solutions is 4.184 joules per gram degree Celsius, or 4.184 joules per gram degree Kelvin. So notice that the values are actually the same, it's just the unit is either degrees Celsius or Kelvin. So calorimetry is really important because this is to measure the heat flow that is associated with an accompanying reaction. So really what we look at here is the delta T. So since we don't know the exact enthalpy of reactants and products, we can measure through the process that's called calorimetry, which looks at heat flow. So we look at heat flowing in or out of a system. This to the left shows your calorimeter. Typically we use 2 coffee cups nested together to provide insulation. You can use a cork stopper. We have cardboard stoppers with a stirrer and a thermometer. This actually works very well for our purposes, so we don't get the expensive calorimeters. We just use the coffee cup calorimeters and they work just fine. So by carrying out the reaction that's in aqueous solution, we can actually indirectly measure the heat change for the system by measuring the heat change of the water, or instead of the water, it'd be the solution in that calorimeter. Typically for an exothermic reaction, we have negative Q reaction equals positive Q of solution or of water. And the way to tell that it's exothermic is that the temperature of your solution increases. Right? The system is releasing energy into the surroundings, so the temperature of the solution increases. For endothermic reactions, you're going to have positive Q reaction equals negative Q of solution or of water. And a way to tell that it's endothermic is that the temperature of the water or of the solution decreases, because the system, typically what you're dissolving, is absorbing energy, so it's pulling energy from the water and it's decreasing the temperature. So when we look at calorimetry, we look at Q equals MC delta T, it's important to know specific heat and heat capacity. We're going to define each of these terms a little bit later, but for now we're just going to focus on specific heat because this is what we use the most. So we define specific heat capacity, or just specific heat, as the amount of energy that it takes to raise 1 gram of a substance by 1 Kelvin or 1 degree Celsius. This is, again, different from just heat capacity, but table 5.2 shows us some specific heats of some substances. And notice that all of the values are different, and that's because all of the substances change temperature when they're heated, but the magnitude of that temperature change varies from substance to substance. So if we look at specific heat, notice water's is the greatest. The specific heat of water being large actually accounts for why oceans are relatively resistant to change, why like California and Florida have a relatively mild climate, doesn't change much. That's because of water's large specific heat. It takes a lot of energy to raise 1 gram by 1 degree Celsius. And so that has the highest. Notice in this table, mercury has the lowest. It doesn't take very much heat at all to raise the temperature by 1 Kelvin or 1 degree Celsius. So an example, you have 2 examples here. The first one says the large beds of rocks are used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82 joules per gram degree Kelvin. Calculate the quantity of heat absorbed by 50 kilograms of rocks if their temperature increases by 12 degrees Celsius. And then B says what temperature change would these rocks undergo if they emitted 450 kilojoules of heat. So what I want you to do is I want you to try this example, but before you go into doing any calculations, I want you to label everything that you are given with the correct variable. So for example, you're given specific heat. So above this I would write C. You're also given 50 kilograms, right? That's mass, so put an M, and it tells you that the temperature increases by 12 degrees Celsius, so this is the temperature change. So go through, label everything, see if you can calculate heat in A, and see if you can calculate delta T in B. So pause the video, do that, and then we'll actually go over the correct answers. So the solution for these examples, like I said, label everything that you are given. So you're given C, you're given mass, you're given delta T, and you're trying to find Q. In this problem, look at your values for specific heat. These will remind you of the values that you need to plug into the equation. So when we have Q equals MC delta T, M needs to be in grams. Notice then the problem it's given in kilograms. So multiply this by 1,000 to get to our mass, because there are 1,000 grams in 1 kilogram. So that's how you convert that. C is going to go directly into the equation, as well as delta T. So you do have to convert mass to grams, but your change in temperature actually doesn't have to be converted because the delta T is actually the same for Celsius and for Kelvin because the ratios are the same. So as long as your delta T is in Celsius, that's actually going to be the same delta T as Kelvin. So when you solve for Q, you get 492,000 joules. It's fine if you want to leave it as 492,000 joules, but typically to make it a little easier, you might see Q represented in kilojoules. So for your answer, you should get 492 kilojoules. And then B says, what temperature change would these rocks undergo if they emitted 450 kilojoules of heat? So again, look at your units for C to make sure that you have everything converted correctly to put it into the equation. So Q needs to be in joules, right? Because C is in joules. So get from kilojoules to joules. Okay? Again, kilo is larger. There are 1,000 joules in 1 kilojoule. So that means there are 450,000 joules. Remember your mass of your rocks don't change, 50,000 grams. You have C, and then you have delta T, and you're solving for delta T. It's asking for temperature change. So you multiply 50,000 and 0.82 together, divide 450,000 by that, and you get delta T equal to 10.98 Kelvin. Now, you can give delta T in Kelvin, you can give delta T in degrees Celsius. Typically, we'll leave it as Kelvin just because that's what is in the specific heat. Okay, so this is going through a question using constant pressure calorimetry, which is using coffee cup calorimetry. That's what we're going to use almost always. There is another type of calorimetry, and it's called bomb calorimetry. Bomb calorimetry takes place at a constant volume. So if you need the volume to stay the same, that's what bomb calorimetry is used for. Typically, you use bomb calorimeters to study combustion reactions because the bomb calorimeter, this is what your sealed bomb calorimeter looks like. The bomb calorimeter actually has an inlet for oxygen, so it allows oxygen in, as well as leads to ignite the sample. So bomb calorimeters are typically used if you're looking at a combustion reaction. because it has to ignite within the smaller cup itself. So this small reaction chamber here is actually considered the bomb. So with bomb calorimetry, the heat that is absorbed or released by the water, just like we looked at before, it's a very good approximation for the enthalpy change. Typically, the Q of reaction is going to be given in kilojoules or kilojoules per mole. And so that's typically what we'll use for Q reaction. To calculate Q with a bomb calorimeter, you have to know the calorimeter constant. So to find Q in a bomb calorimeter, you use Q reaction equals negative C calorimeter. It's the specific heat or the calorimeter constant times the change in temperature. So this is a little bit different than Q equals MC delta T that we looked at before. So because the volume is constant, what's really being measured is internal energy, not delta H, but the difference is so very small that we even ignore the possibility of measuring internal energy and we just focus on delta H. So this is looking at a bomb calorimeter. Again, we don't use this very often. We're going to look at some examples just so you know how it works, but typically we're going to use Q equals MC delta T. So looking at the differences in all of these vocabulary words, to start off we have heat capacity, which is just C. Heat capacity is very general. It's just the amount of energy required to raise the temperature by 1 Kelvin. So it's usually just joules per Kelvin. Molar heat capacity is going to be heat capacity, but in terms of moles. So it's the amount of energy required to raise the temperature of 1 mole by 1 Kelvin. And then specific heat capacity, or just specific heat, is the amount of energy required to raise the temperature of 1 gram by 1 Kelvin, or 1 degree Celsius. And then we have the calorimeter constant, which is C with a lowercase c as a subscript. And this is the heat capacity of a calorimeter. So it's just how much energy is required to raise it by 1 degree Kelvin. Again, temperatures can also be in degrees Celsius because those ratios are the same. But looking at heat capacity and specific heat, we will deal with specific heat much more than anything else. So we typically look at the energy needed to raise 1 gram by 1 Kelvin or 1 degree Celsius. So looking at enthalpy along with stoichiometry, so we're going to start bringing stoichiometry back in. This is a lot like algebra. So because enthalpy is an extensive property, changing moles or the mole ratio changes the value of delta H. So think about it like algebra. This top reaction is, we can say, our general reaction. To get from the first to the second, what do we have to do to everything? Well, we're multiplying everything by 2. So if we multiply everything in the reaction by 2, we also have to multiply delta H by 2. Okay? Or if we go from the first to the third, notice we're dividing everything by 1/2. Well, when we divide everything by 1/2, we also divide delta H by 1/2. So if the coefficients are multiplied by any integer or any fraction, delta H is also multiplied. If we were to flip the reaction, if we were to flip this and make calcium carbonate the reactant, then we're going to flip the sign of delta H. So this, instead of being negative, would become positive. So this is very useful for us to get into Hess's law. But what I want to do first is show you how delta H can be used within stoichiometry. So this is how much heat is released when 4.5 grams of methane is burned in a constant pressure system. So we have an amount, and we want to know how much heat. Now notice we don't have delta T, we don't have C, but we have this thermochemical equation. We have the balanced equation and we have delta H. So notice that from this balanced equation, for every 1 mole of methane that we burn, 802 kilojoules of energy is released. This can be used as a conversion factor, All right, 1 mole of methane equals negative 802 kilojoules. So what we can do is set this up like dimensional analysis. 4.5 grams, convert to moles. Remember, when all else fails, convert to moles first. So convert to moles of methane. Then we can use this for every statement right here, right? For every 1 mole equals negative 802 kilojoules. We can use this as a conversion factor. So grams cancels, moles cancel, we're left with kilojoules. Okay, so as we go through, here we go, we have 226 kilojoules. Now take a look at this, and there's one thing that's missing. Okay, do you see what is missing? Okay, there is a negative missing right here. Now the reason that it's not here is because there's 2 different ways that you can actually represent an exothermic reaction. We could put the negative here and say negative 226 kilojoules, or we can say 226 kilojoules released. Either way will work, but you have to make sure that you use one way or the other so you can tell that it's exothermic. Okay, so now we mentioned Hess's law before. Now the reason that Hess's law is important is because delta H is known for many reactions, and it's pretty inconvenient to have to use calorimetry to measure delta H for every single reaction that we're interested in. But what we can do is we can estimate delta H using known values because it's a state function. So Hess's law is what kind of determines how we go with enthalpy and how we work with delta H. And Hess's law states that if a reaction is carried out in a series of steps, delta H for the overall reaction will be equal to the sum of the individual steps. So what this is saying is delta H overall equals delta H of reaction 1 plus delta H of reaction 2 plus delta H of reaction 3, and so on. Because enthalpy is a state function, the total enthalpy depends only on initial, which is the reactants, and final, which is the products. Delta H is the same whether the reaction is one step or whether the reaction is a series of steps, and that's because it's a state function. So Hess's law provides a useful means of calculating energy changes that are difficult to measure directly. And it's going to be very useful once we get into an equation that's made up of 5 different steps. Hess's law makes it very easy for us to calculate delta H. So let's look at calculating delta H using Hess's law. Now think of this like a system of equations. Okay, this is essentially what Hess's law is. It's a system of equations. So you're given however many equations. In this example, we're given 2 equations. We have carbon and oxygen reacting with CO2. We have carbon monoxide and oxygen reacting to form CO2. And then we have the delta H values for each. And then this says find delta H for the following. So now we want to find delta H for C plus 1/2 O2 yields CO. Now, when you are working with Hess's law, there will be times that you could potentially have 5 or 6 reactions. To make your life easier, what I always recommend doing is get the reactants that you need, okay, on the left side, the products that you need on the right side. Then let everything else kind of fall into place. So to start, we need carbon on the left. Okay? Here is the only reaction that has elemental carbon. It's already on the left-hand side. So I'm going to leave this reaction alone. But we need CO. Okay, I'm going to skip oxygen because notice oxygen is here and oxygen is here. So I'm going to skip that for now. But we need CO on the right. And here carbon monoxide is on the left. So what I'm going to do is I'm just going to flip this equation completely. So here we have carbon and oxygen and CO2, and then I flipped the reaction to get carbon monoxide on the right. Notice when I flipped the reaction, I flipped the sign of delta H. So now what I'm going to do is I'm going to cancel out whatever's on the left and on the right, just like algebra. If you have something on the left, you have something on the right, they'll cancel out. So I have one CO2 on the right, I have one CO2 on the left, those are going to cancel. I have 1/2 oxygen here, and initially, 1 oxygen here, right? But I'm going to cancel out half, and that gives me 1/2 oxygen here. So now, let's just go back through and double check this. I have carbon plus 1/2 oxygen yields CO. That's what I want, right? Treat it like a system of equations. Then we just add up our delta H values. So delta H equals negative 393.5 kilojoules plus 283 kilojoules, and that equals 110.5 kilojoules. So again, it's like a system of equations. If we have the same thing on both sides, we can cancel. If we need to multiply, we'd multiply by our delta H. In this case, we don't have to do any multiplication. We just had to flip the sign of the second equation. So this is looking at Hess's law. What you will find is you will find additional videos going through Hess's law, going through calorimetry problems, just to help out, give you some more examples. But then in class, we will do many, many more examples to help you with Hess's law and help you with calorimetry.